Hello friends. So today I'm going to discuss two problems which are related to binary search, right? So I'm going to discuss the brute force and the very optimized approach for solving these problems. I've taken up these problems from Scalar platform, okay, and I will try my best to explain the approach. Okay. So let's discuss the first problem. First problem is the search for a range, right? So problem states that we are given a sorted array of integers which are zero indexed, and we need to find the starting and the ending position of an integer b in the array. And if it is not found, then we return -1 and -1. So we need to return an array of size 2, which is having the starting and the ending. You could say the position, like starting and the ending index of the integer b in the array A. Okay. So let's just go over some examples. Like, for example, if we are given this array, so we will be given the sorted array. What that means is that all the similar elements will be grouped together. So, for instance, if we are going to find the target 8, so we can see that all the 8s will be grouped together in the sorted array. Now we need to return the starting and the ending where this 8 starts and where this 8 ends in this array. As we can see that this 8 starts at index, we could say 0, 1, 2, and third index it starts and it ends at the fourth index. So the output is 3, comma 4. Now in the second example, if we say like we are given this sorted array and we need to find the starting and the ending position of this 3, it is not present in the array. So we return -1, both, right? So the very brute force approach which comes into picture is like is that we need to return the first and the last occurrence, right? So initially we will initialize them like with minus. We will consider that we haven't found the target. Let's say our target is 8, so we haven't found our target in the array yet. So the brute force is the linear search, right? We can simply apply the linear search. We go ahead with finding the target element in the array. We will compare if is this my target element, it is not. We will continue. If is this my target element, it is not. Is this, it is not. As soon as we find it, right? Like this is going to be our first occurrence. As soon as we find it in our array, so we can determine that this is the target element's first occurrence in the array index. So we initialized our first occurrence with that index. Now we need to find the end index. So we have this thing like, okay, so now all the target elements will be grouped together. So ultimately, as we will be continuing in the array, we will always encounter this target element till the time it is present in the array, right? If there are multiple duplicates present for this target element, we will continue encountering it. So what we can do is that now after finding the first occurrence of this element or the target, we will look for the end occurrence. And how we will be determining the end index for this array is by checking the position where we are not able to find this target, right? By checking the position where we are not able to find this target. So first we found the target, we are good to go, we found the first occurrence. Now we know that it is going to repeat itself if it is present multiple times. So we will continue in the array till the time we don't find it anymore. And as soon as we encounter that index, right, we will store the end index, and that will be the index where it was not found -1, right? Because at that particular index, we found that the target is no more, repeating. So we can say that before this, it was actually repeating itself. So that was its last occurrence. So we will update our last occurrence with that index and we will break out of the loops, right? So this is what I thought in the brute force approach, right? To like I will be coding my own way of brute force approach. You can go ahead and apply your own code of or do your own code of applying the brute force approach, right? So first of all, what I'm going to do is I'm going to get the length of the array A, which is given to me. I'm going to first check that if the length is equivalent to 1, right? As the constraints are said that the array size is greater than equal to 1, it is not going to not it is not going to be empty. So I'm just going to check it for once, like if it is equivalent to 1, then I'm going to check that if that it states that only one element is present, so I'm going to check that whether it is equivalent to my target element or not. If it is my target element, then I can simply return the first index. And if it is not, then I can simply return -1 and -1. Right. So this is checking the for the condition for array size equivalence to 1. You can feel free to write a code which actually handles this case within itself. I'm just I like to uh, do away with the edge cases first time. Right. Now let's just initialize the values as -1 and -1. So this is the, you could say, this is actually my first occurrence, and this is stating my last occurrence. Right. I'm going to initialize a variable with 0, and I'm going to loop over in the array while I is less than length of the array. Right. Now I will be continuing inside this array. I will be checking for the first occurrence. We need to check when the element is coming in array. So we will compare like when is the element is becoming equivalent to my target. As soon as it becomes, I update my first occurrence with index. Right. Now my last occurrence, I can like now I need to iterate in array to find the last occurrence or the final final occurrence of this. So what I'm going to do is I'm going to initialize another variable j, which is going to check from I itself. And while j is less than length of a, right, I'm going to check now till the time my a of j is not equal to my target. Right. This condition not equal to is due to the reason because we know that in the sorted array all the targets are going to come together. So we are finding till the target is not repeating itself. Okay. Finding the position till the target is not repeating. So when as soon as we find that position, what we need to do, we need to update our last occurrence, which is actually going to be the position -1. Right, the j -1. Like in here, as soon as we come at 5, we will find that it is not equivalent to my target. So I will be updating my last occurrence with 5 -1, that is 4. Right. And I can simply easily break from this loop. And else, if it is not, if it is still repeating, I will continue in the loop. Right. There is one more edge case which is, needs to be handled in this, right? And that is like, for example, let's just say that if my target is actually repeating till the end as well, what will happen is that if this is the situation, my loop will get over, right? And I won't be able to update my last occurrence. So I need to check if my jth index is equivalent to length of array. That means it reached the end of the array. It means that my target is actually repeating till the end, right? So if my jth is equal to length of the array, right? We are by jth we are finding till what position it is repeating itself. So if my jth is equivalent to the length of the array, that is the end index of the array or where the array is ending, right? It means that my target is actually repeating till the end. So at that position, at that point, I need to update my last index with len a -1. Right. This is one of the edge cases that needs to be handled for updating the last occurrence of this element. Right. And we can simply break off of the outer loop as well. And in the outer loop, till the time I'm not able to find this element, right? Till the time I'm not able to find the first occurrence of this element, or my target, I will continue looking for it. And at the end of the day, I am going to return my first occurrence and the last occurrence. Right. So this is what we did here, and let's just see that if it works or not. So right, it passes all the test cases. Right, it is passing all the test cases. So this is working fine for us. Right, and let's just see that if it will work for all the things. But before that, let's just consider what is the time complexity for it. Right? What is going to be the time complexity? So as we can see that we are having two nested loops, where one in the other. So if any person would think like, okay, we are having this loop and then we are again looping. So what some of you might be thinking that it is n square, but it is actually not. So the time complexity is actually going to be n for this particular approach. And the reason being is like if we consider this example itself, right? Let us say this is the array. So as we are looping in for finding the first occurrence, our I is starting at this position, right? Our I is starting at this position. Now our I index is not equal to the target, so we increment our I to the next, right? Now our I is here. Again, it is not equal to target, we increment our I to next. Again, it is not equal to target, we increment our I to next. As soon as it becomes equivalent to target, what happens, we go inside the if loop, right? We initialize our j with I and we continue to find its last occurrence, right? So now at this position I, we are actually also initializing our jth, and we will continue within this loop to find the last occurrence of 8. So when j will start here, we will find that it is equivalent to target. Right. But our condition is to check if it is not equal to target. So we will continue. So again, j will be incremented from here to here. Again, it is equivalent to target. So we will again continue. So j will be incremented to this position. Now it is not equal to target. Right. Now it is not equal to target. So we encounter this if condition where we update our last occurrence with j minus I and we break. And as soon as we break from this while loop, since our j is not equal to length of a, then we will come out of like this if condition won't be executed, and then we will again break from the outer ith loop, right? So ultimately, how many times we are actually traversing each element in this array? One, right? So the time complexity is going to be n, where n is the size of array. And what is going to be the space complexity? Since we are only utilizing two variables, right, and no extra space is being taken, right, our space is not increasing with the input which has been provided to us, we can simply say that our space complexity is also 1, right? So time complexity is n and space complexity is 1. So I want to focus on this time complexity. Now this time complexity is n, which is dependent on the actually the size of the array. According to problem constraint, it will pass all the hard and the easier test cases because our size of the array is 10 raised to the power 6. 8. Our size of the array is 10 raised to the power 6. So linear approach will definitely work. But what if the size of the array can be 10 raised to the power 9? In that situation, our array, like this linear approach won't work. Right? We need to come with certain optimization. So the next optimization which we are going to discuss is the binary search, right? So this is the binary search approach. So now what actually binary search states, right? What actually binary search states? Objective of binary search is actually to search an element in the, in a certain search space, but major thing which we are doing is we are discarding a certain portion of that search space, or we could say by half. That is what binary is, like by 2. Binary considered by 2. So right, it's like we are discarding a certain section of a search space based on a certain condition. So let's just go ahead and look into what condition that could be. Right. So the main concept behind binary search is like first we need to determine the search space. Our search space is basically where we are going to find our answer, and it is definitely lying inside this array itself, the index. Right. So the concept is that we initialize a start and an end. Right. This right is going to be basically equivalent to the length of the array. We initialize the very first, the position where it is least probable to find, and the position where it is most probable we can find this element, right? We can either find this element at the index 0, or we can either find this element at the index length of array minus 1, that is at index 5, right, our target element. So we start with the middle index. We find their middle index by performing this operation, right? And we discard, and we continue to discard the search space. So let us see how it will work. Let's just consider this array itself, and our target is 8. Okay, we will be having the first and the last occurrences minus 1 only. Okay, so now our left is initially 0. Our right is actually length of array minus 1. What is the length of array? Length of array is 1, 2, 3, 4, 5, 6. 6 minus 1, that is 5. So our middle will be 0 plus 5 by 2, that is 2, right? So the middle will be 2. Now we will check whether our second index is it equal to the target? It is not, right? It is not equal to the target. So now we need to observe, right? Our mid is not equal to target, but actually it is less than the target, right? So can we say that is since our mid, right, this position, it is less than our target, the element in this position is less than our target, so I won't be able to find my target before this index, right? I won't be able to find my target before this middle index too, if you would consider, because since this middle index element is itself smaller than my target, how come I can find it before this? So I need to search my target after this middle index, right? So how can I move forward? Search in afterwards direction, in the forward direction. What I would do is I will increment my left with mid plus 1. So now my left is going to be 3, my right is going to be 5, and my mid is going to be 5 plus 3 by 2. 5 plus 3 by 2, that is 8 by 2, and that is 4. Right. Now we will again check whether my middle element, right, whether my middle element, let me just write that condition, right? What are the possibilities? The array mid element can be either less than my target, it can be greater than my target, and it can be equal to my target, right? So in each condition, we will need to check what steps needs to be taken. So here it is actually equal to my target. At condition 4, we can say it is equivalent to my target, right? So we can say that, right, my mid index is now equal to my target. Now what to do? Right. Now what to do? Now we have found our target element in the M. Now we need to find what our objective was. We needed to find the first and the last occurrence of the element. So can we say that, can we now deduce anything from this? Like whether it is our first occurrence or the last occurrence? Can we say that this is our last occurrence, or can we say that this is our first occurrence as soon as we find middle element equivalence to the target? No, we cannot, right? We just cannot find it, because how do we know that if it is even my last occurrence of this element or not, right? So we will, what we will do is we divide our, this search space, like we will actually split this thing into two sections. One section would be to find the first occurrence of the element in the array, and the second section would be to finding the last occurrence. So if we are considering the section 1, right, if we are considering to find the first occurrence, this, that is section 1, finding first occurrence. So if we need to find the first occurrence, we need to find our first occurrence will always be coming, you can say towards the left hand side, right? We will always need to move towards the left hand side to find the first occurrence. So as soon as the middle is equivalent to target, what I am going to do is I'm going to, you know, first of all, I can say that this can be my probable answer, right? I can say this is can be my probable answer. So I will update my first occurrence with mid, right? And now the second thing is like I need to go left. And how did we went left? How do we go left? Basically, is by decreasing my right point. So what I was going to do is I'm going to decrease my right to mid -1. How this is going to affect is you are going to see the here. So now currently my left is 3 and my right is going to be mid -1, and that is equivalent to 3. So right, so 3 plus 3 is 6. 6 by 2 is again 3. So as you saw, right, our mid actually decreased as we decremented our right. So we moved left. Now again we will check whether my mid is equal to target. Yes, it is. Again, my mid is equivalent to target. So again, my I will update my first occurrence with that mid index, and again I will follow the same approach. I will continue to look in the left direction for the first occurrence of this element. Right. So my right left is 3 and my right is now going to be, this is a interesting part, right? My right is now going to be mid -1. That is 3 -1, that is going to be 2. Right. Now we require a breaking condition in this. If you are already knowing binary search, then you will be able to follow up in this. Like in binary search, we definitely have a certain breaking condition where we actually come out of the loop. It can be as soon as we found the element, or it can be here. It will be like as soon as my left is greater than my right. You know, as soon as my left is greater than my right, I will break from the loop, because this is the condition where my search space is empty now, right? I can no longer search in any direction, so I will be coming out of the binary loop or the binary search loop. And as you could see, my first occurrence is being actually updated by mid, which is 3. So now I am actually having my first occurrence as 3, and the similar approach we are going to follow to find the last occurrence. But what is the catch here, right? Like how we are actually going to, find this last occurrence in the array. Let's just see, right? So let me just delete that. Right now we will need to find the second section, which is the last occurrence of this element. So we will again running this binary loop, keeping this condition in mind, like till the time our left is greater than right. Oh, sorry. Keeping in mind that till as soon as my left is greater than right, I will break from the loop. So I will initialize my left again to 0, my right again to len a -1. My left is going to be 0, my right is going to be 5. My left is less than right, so I can continue in this loop. I will again find what is the mid. So my mid is going to be 2. I will compare whether my second index is actually equal to target or not. It is not. So my mid is actually less than target. So what I need to do is I need to search on the right hand side again. So I will increment my left with mid plus 1. So my left is going to be 3. My right is 5. And my middle element index is now 5 plus 3, 8 by 2, and that is 4. Right. Now fourth element index, we can say our mid is now equal to target. So now instead of updating the first occurrence which we have already found, since we are going for the last occurrence, we will update our last occurrence with mid. And since we are finding the last occurrence, we will always going to search towards the right. the rightmost occurrence of this target. It is going to be the last occurrence of this target. So to go right, we will update left where mid plus 1. So mid is going to be 5. Oh, sorry, the left is going to be 5. The right is again going to be 5. And what we found was mid is 5. 5 plus 5, 10. 10 by 2, 5. Now at index 5, we can see that the integer value is greater than my target. Right. That means in the sorted array, if this integer value is greater than my target, that is 8. So my target actually lies on the left hand side. It is greater than target. So my target actually lies on the left hand side. So to go left, what we did was we updated right with mid minus 1. So right is going to be mid minus 1, that is 4. My left is going to remain same. And now observe this, like our left is greater than my right. So this is the breaking condition. We need to come out of the binary searching. So we found that our last occurrence of this element is actually 4, right? Last occurrence is actually 4. So we found the first occurrence, we found the last occurrence, and we found our answers, and we are going to return them. So this is how binary search will work. And the best part is, like, if you know, the time complexity in binary search is actually log of n, right? Time complexity is log of n, and the space complexity is also going to be O of 1, because we are not taking any extra space in it. Simply searching within this binary, like this array, and we are finding the first and the last occurrence, right? So let us just optimize our approach here. Great. So what first we are going to do is we are going to remove this. We will be having this length of it. Let's just initialize a start index which is 0, an end index which is length of a minus 1, first occurrence minus 1, and last occurrence is also minus 1, right? So my loop will continue, right? It will continue till my breaking condition, right? That is, since I put this condition like left is greater than right, we need to break from the loop, or I could say that the my loop will continue till the time my left is less than equal to right. And I will continue searching in the array till the time my left is less than equal to right. So till the time my start is less than equal to end index, I will continue in this array. It will actually handle automatically the condition where I need to break when left becomes greater than right, or the start becomes greater than end, right? So now I need to find the mid position, which is going to be start plus end plus start by 2, right? This is going to be mid position minus start by 2, right? This is one way of preventing a certain a value or limit overflowing from the type. Basically, since our a of I, or you could say the array of, if we are considering the array size to be 10 raised to the power 9, right? So our index can be huge. So if we add, right, two indexes, it can actually go farther than 10 raised to the power 9. So to prevent that thing, we are utilizing this thing. It is equivalent to the same thing, which is left plus right by 2, or you could say start plus end by 2, right? It is equivalent to that thing only, right? So now we need to check for the condition, like if, like, first we are going to find for the first occurrence. We are going for the first occurrence, so we will check, like, if my area of mid is less than target. If my area of mid is less than target, that is B, what I need to do, I need to move to the right hand side. So my start will be incremented by mid plus 1. Else, if my area of mid is greater than my target, then my definitely my end needs to be, or I need to search on the left. So my end needs to be incremented. Or else, This condition is where our target is or the mid index is equal to my target. So at this position, I will save my first occurrence, right? I will save my first occurrence, and since I need to find the first occurrence, I will continue to search on the left. And to go left, here we are going left, here we are going right. To go left, what we do? We do end equals mid minus 1. This is actually, this loop, complete loop is actually going to terminate as soon as my start becomes greater than my end index, right? And it will also update my first occurrence of the element. Can I just make a small change here and then find the end occurrence as well? Yes. So my end occurrence is going to be, the first two conditions are going to remain same. Only thing which is going to change here is the last occurrence of my element, and since we are finding the last occurrence, I am going to go to the right. So my start is going to be mid plus 1. That is just the small change which is going to happen here. And since my start and end has changed previously, so I need to reinitialize them. That is going to be length of a minus 1. Right. So here we found the first occurrence and the or do you could say the last occurrence. And since we have found them, we can simply return the first occurrence and the last. Best part about this is it will work for events array sizes which are further greater than 10 raised to the power 9 as well, because the time complexity is going to be logarithmic. So if we test it, right, it is passing all our test cases, right? And let's just see if it is, we submitted, if it pass all the hard test cases, and it did, right? So this is one of the questions which we solved with binary search, like search for the range. Now let us discuss the second problem, right? Second problem is also interesting, which is finding the square root of an integer. So in order to find the square root of an integer, it basically states that not all integers are perfect squares, so we can actually return the float. So what it means is like the nearest square root, or the number which can actually give the nearest square root to the number. So we can actually return that. This is what it means by square root of a number, right? So very first thing is the which we can observe, right? Let us just discuss the brute force approach in here, right? And I can just discard the above approach. I hope you understood everything till this time. Right, so now the square root of an integer, the brute force rule. So brute force is simple. Like first observation is we know that the square root of a number is always going to be smaller than the number. That is, we are 100% sure about that. That the square root of a number is always going to be smaller than it. Right. Let me just go through one example as well to make it clear for you, like what is meant by the floor of square root of it, if you are not clear about it. So the nearest square root which is equal to, the number. So like for example, 11 is not a perfect square, right? So 3 is the output. That is because if we consider 3 squared, that is 9, right? And if we increment 3, we get 4. And 4 squared is actually 16, which is greater than 11. So this cannot be our answer, right? It is becoming greater than 11. So the nearest square which is coming, just smaller than 11 or equal to 11, that is being given by 3, right? So that is meant by floor. And since 9 is the perfect square, so we are returning its value as 3, right? So again, back to the thing. So linear approach, right? So linear approach is basically, we know one observation is that the square root of a number is definitely going to be smaller than the number. So the simple thing is, why don't we just run a loop from 1 till the number itself, right? And keep on checking for every number, multiplying it by itself and checking whether it is equivalent to my target or not, right? And as soon as it becomes greater than my target, I break. Right? As soon as it becomes greater than my target, I break. So let's just implement this linear approach, right? This brute force way. So what we do is, like, let's just create a variable which is storing my answer, and let me find the length of this array as well. Right. So for I in range length of, or let me just consider a while loop. While I is less than length of a, and a of, right, let's just do this way, right, while till the time my index is less than the length of the array, right, I'm going to check whether if a of I times a of I, right, if a of I multiplied by a of I, or you could say, sorry, I'm since I'm checking, right, so my I is going to be 1, I'm going, and A is not an array, so sorry, so A is my target, right, so I is 1, A, let's just say it is 11, so I will continue till the time 11, I is equal to 11, as we have discussed here, right, till the time we start from 1 and we go till the target. So till the time my I is less than equal to my target, I will check if I times I is less than equal to A. Or let me just push this in a more appropriate manner. Let me just consider I times I till the time, right? Till the time my number square is less than the target, I can definitely update my answer, because we need to find the nearest square if it is not a perfect square. So the nearest square can definitely be till the time the number square is less than the target. So I will keep on updating my answer. Right. And as soon as my I time I is become greater than this A, it will automatically come out of this loop. And I also need to increment my I. And then I need to return my answer. Right. If I go ahead and test it, I'm not sure if it is going to pass all the test cases or what kind of test cases is going to be given in there. But yeah, it passed all the test cases because those are all easier test cases which is provided. But when I will submit it, it will definitely going to fail. The reason being because this is a linear approach, and as you can see the constraints, right, our number can be huge. So a linear approach which is having this huge amount of number, had it been the range of A, B, 10 to the power 6 or 7, right? So this approach would have worked. Definitely it would have worked. But for this huge number, it will definitely fail. So again, binary search comes to our rescue. Let's see how we can apply the binary search here. Right, let's just see just how can we apply the binary search here. Right. So the linear search approach is definitely, you must have guessed, it is actually going to be equivalent to the target itself, the time complexity. But to be honest, like the time complexity is actually going to be floor value of square root of my target. Right. If you thought that it was equivalent to the target or something, like, it is wrong, because we are not actually going to go till the target, because our while loop is definitely going to end as soon as the square of my number becomes greater than target, right? So it is actually going to be square root. If it is a perfect square, then it is going to end, like, loop is going to end in the square root itself, and if it is not, then it is going to end in the floor. Space complexity is definitely one, because we are not utilizing any extra space. Now in the binary search, right, how can we reduce this time complexity actually in the binary search? Which is, this is approximately, you could say, equivalent to n, or you could say a linear search approach. So if it is 10 raised to power 10 or number, right? So it is something like that. It is approaching that thing itself, right? So let's just see that how can we optimize this. So the binary search approaches we first determine the search space. Search space is basically in what kind of range we are going to find our square root. So we know that like as we discussed, our square root is always going to be smaller than the number itself. So it is safe to say that our square root is going to lie within one and the target itself. So that is the space in which we can search, right? So the concept is like we start from one, the end index, or you could say the end value is going to be the target itself. We again find the mid, and now what we are going to do is we are going to check whether our mid element is target, the mid element squared is actually less than or equal to target or not, right? If it is, we update the answer. If as soon as it becomes greater, right, or you could say or basically if it is not, we continue, right? So what actually will happen is, let me just consider one example. Let's say my target is 11, right? Let's just see how we are going to proceed. So what we are doing is we are checking for the mid, again the same approach as we found earlier. Like we find the mid, we check whether it is less than target. If it is, then we update the answer. And either like I don't think so like we need to take for this, but as soon as my start becomes greater than my end, I will definitely need to break from my loop, right? So let's just consider the situation where we are checking for the target, that is 11, right? So we are going to check for 11. Now my start is going to be 1, my end is going to be 11, my mid is going to be 11 plus 1 by 2, that is 12 by 2, that is going to be 6. Now I'm going to check whether 6 times 6, 6 times 6, what it is going to be. It is going to be 36. So now it is basically greater than my target. It is very greater than my target. So I need to reduce my search space. I need to reduce my search space towards the left. So what I'm going to do is I'm going to, as to reduce it, I'm going to do a mid minus 1. I'm going to decrement my end index with mid minus 1. Like in the previous approach, since we are going to move left, right, we were moving left. So we decremented our array with left equals mid minus 1. So similarly, here we are also, since we need to move to the left, we decrement our end index with mid minus 1. You can consider this similar to array itself. Like we are given an array till the target, like 1, 2, 3, 4, and it is continuing till 11. So this is our array, or this is our search space. You can consider, you can take this reference. So since we found 6 right here somewhere, like 5 and we found 6, right? We found that our condition is not matching. Our condition is actually becoming, the square is becoming greater than the target itself, that is 11. So definitely the number square which is going to be less than the target is actually going to lie on the left hand side of this, right? The number whose square is going to be less than my target is actually going to lie on the left hand side of this, right? Because if I move further right from this mid, like if I go to 7, my square is definitely going to increase. So I need to go to the left, right? So to go to left, we decrement end by mid minus 1, end by mid minus 1. So my start is going to be 1, my end is going to be 5, my mid is going to be 5 plus 1, that is 6 by 2, that is going to be 3. Now again we will check like whether my 3 cross 3, like this 3 multiplied by 3, that is 9. Is it less than equal to my target? Yes, it is less than equal to my target, that is 11. So we update our answer by 3, right? We will update our answer by 3, but we will what we will do is like we need to find the largest number which is equivalent to my target, right? We need to find the largest number which is equal to the you could say my target, like. So again what I need to do is at this situation, since we need to find the larger and the larger number lies on the right hand side. So what we will do is we are going to move to the right hand side, right? And how do we move to the right hand side is as simple as left is going to be my mid plus 1, right? My left is going to be mid plus 1 because I need to search to the right. So I increment by start, or you could say my start is going to be mid plus 1, that is start is going to be 4. Now end is 5. 5 plus 4, 9 by 2, that is 4. Now we will check whether 4 times 4, 4 cross 4, which is 16, whether it is less than equal to my target. It is not, it is greater than my target. So the thing is that since it is greater than my target, I need to go left. Then I again need to do end minus 1. End equals mid minus 1. So my start is going to be 4, my end is going to be mid minus 1, that is 3. Now observe here, my start is becoming greater than my end, right? So that is my breaking condition, right? So as soon as my start becomes greater than my end, I will break from the loop. And ultimately, since I stored my answer, I am getting as my answer. Had it been 9, so what would have happened, right? Had it been 9, right? Let us just consider 9 here. So our end is going to be 9. 9 plus 1, 10 by 2, that is 5. Now I'm going to check whether 5 times 5 is less than my target or not. So 5 times 5 is actually greater than my target. Oh, sorry, 25. 5 times 5 is 25, which is very greater than my target. So I need to again reduce my search space, go to left. How I go to left? I decrement my end by mid minus 1. So my start is 1, my end is going to be 4, right? Mid minus 1, that is 4. 4 plus 1, 5. 5 by 2. Let me just remove them. Right. So 4 plus 1 is 5, and so, right, now 4 plus 1 is 5. 5 by 2 is 2. Now again I'm going to check 2 times 2 is equals to 4. Now it is actually less than my target. What I need to do, I need to go right now. So I will increment by start by mid plus, because I will find the number whose square is actually equivalent to my target on the right hand side, because currently since this number is giving my target, this number square is giving my this is less than my target. So before these numbers, all the numbers who are having the squares will be having the square less than the target. So basically I will update my start with mid plus 1. So now my start is going to be 3, my end is now 4. Now 4 plus 3, 5, 6, 7. 7 by 2, that is 3. So 3 cross 3, which is now 9. It is now equivalent to my target, right? Since this is equivalent to my target, right? What I am going to do, I will update my answer with 3. And since I need to find the largest, the largest possible, I will again move to the right. So I will increment by start 1, mid plus 1. you know the farther or the farthest like the largest number which you can find, the whose square we can find closer to the target. So start is going to be mid plus 1. Now start is what? 4. End is what? 4. My mid is going to be 4 plus 4, 8 by 2, that is 4 again. Now 4 cross 4, that is 16. 16 is greater than my target. So I am going to what I'm going to do, I'm going to move to the left now. So my end is again going to be mid minus 1. End is going to be mid minus 1. So my end is now going to be 3. My start is 4. And we have actually encountered the breaking condition where start became greater than my end. So we break out of this loop. And thus we found the answer as 3. Okay. So let's just apply this binary approach then, how we are going to move. So let us say the start is 1, my end is a, right, and my answer is 0. So till the time my start is less than equal to end, right? Till the time my start is less than equal to end. Here my start and end were equal. I was still checking. So till the time my start is less than equal to my end, I will find the mid position, right? So the mid position is going to be start plus n minus star by 2. This is again to avoid the overflow condition of the integer, right? Now I'm going to check if my mid squared, right, mid multiplied by mid is actually less than equal to my a. If it is, right, if my square of the number, right, if my square of the number is less than target, like here we forgot to update. I'm so sorry if I need to do that. So here we forgot to, my square of the number is was less than target, so I need to obtain that this is could be my possible answer, right? Here also my square of number is less than equal to target, so this is could be also be my possible answer, and accordingly we proceed. So till the time my square of the number is less than target, this can be a possible answer. I update my answer by mid, and I again move to the right, search on the largest number which I can possibly find. So I would, what I would do is I would increment n by mid plus 1, and else I would decrement by mid minus, oh sorry, end by, sorry, I'm going to increment, right? So I'm going to start is going to be mid plus 1, right, as here, and else if it is greater than, then definitely I will reduce my search space by decrementing it by end by mid minus 1. Like I'm going to search to left, go left, here I'm going right, right, and answer is being stored here. Okay, so now we break out of the loop as soon as start becomes, greater than end, and we can easily return our answer. Let's just see, right? So it is a correct answer. It is working for us, and if we submit it, it will pass all the easy and the hard test cases, right? That's what it is about. So the time complexity, the best part here is like it is going to be log of n, and the space complexity is again constant. So we reduced it from the very linear time complexity to the logarithmic time complexity, and it is the best approach to find the square root of a number, right? So I hope you found this video useful, and you learned from it like how can binary search be applied, which is simple searching algorithm to actually find or solutions to such problems, right? Thank you.